Log on, tune in, find out. Another good idea from Cambridge.
Our speaker is Gutowski, and he is going to talk about novel geometries from near horizon solutions.
Okay, well, I'd like to thank the organisers for giving me the opportunity to present this work. I'm going to be talking about some reasonably recent work done with Ulf Gran Chalmers and George Papadopoulos at King's. The outline is this. I'm going to briefly summarise what we know about supersymmetric black objects in 5 dimensions. So I'm going to start with this as a sort of gentle introduction, because the aim of the game is to understand the general structures, the general geometries associated with black holes in more than 4 dimensions. Of course, this is particularly interesting in the context of string theory, and the first dimension in which things start to become noticeably different from 4 dimensions is in 5. Then I'm going to describe some interesting geometric structures which appear not in the context of 5 dimensions, but in what I'm going to discuss today in 10-dimensional type 2b supergravity. And so these are the geometric structures: strong Kähler with torsion and strong Calabi-Yau with torsion manifolds, which I'm going to discover along the way. I'm going to summarize briefly the supergravity I'm going to be looking at, 2b supergravity, and how to analyze supersymmetric solutions, in particular supersymmetric black hole near horizon geometries in this theory. And then I'm going to describe the analysis that we did and give some examples of solutions. So in terms of examples, it turns out there's a lot of geometries which are the form ADS times some warp product of ADS with some other internal space can be recast as near horizon geometries, as I'm going to describe, and we can find a very natural geometric structure which all of these lie within. It's, in a sense, it's a kind of hidden geometric structure, and I'll describe what I mean by hidden as well. And then I'll end with some conclusions. So the reason we're interested in black holes in high dimensions is of course, for string theory, one reason, and also because black holes and black objects, as I should more accurately refer to them, behave differently in 5 dimensions than 4 dimensions. So in 4 dimensions, we know that there are strong uniqueness theorems due to Hawking, which constrain the topology of the event horizon, and so it has to be basically S2 topology. You can't have S1 times S1. But in 5 dimensions, you can have more interesting things in terms of exotic topologies. So if I take minimal gauge supergravity in 5 dimensions, which is Einstein-Maxwell with the Chern-Simons term, there are a number of different solutions, all of which are asymptotically flat. There are the BMPV black holes, and these have horizon topology, which is S3. And now we have the black ring solutions. So these are in addition to the black holes, and these have different horizon topology. There's a horizon topology which is S1 times S2, and these are due to Harvey-Rial and others. And you can even have combinations of the two. You can have so-called black Saturn solutions, first constructed by myself and Jerome Gauntlet, and then Emperor. Yes.
How Figueres and collaborators were they not the first people to use black Saturn? I mean,
okay. So well,
because I thought you had concentric black rings rather than. I mean, maybe there is the same.
Okay, so in terms of black Saturn, I'm really interested in the horizon structure.
Okay.
So we found the first black Saturn in the sense of a black object which has an S3 horizon in the middle and S1 times S2 around. They found so 2 years after this one, there came the vacuum solutions. It's actually it's easy. It is true that it's easier to find the supersymmetric solutions. So those are the ones that we found first. But then you have to do a bit more work, unfortunately, when you look at the vacuum solutions. But these exist both in supersymmetric and non-supersymmetric variants. So, how can one hope to get a handle on these types of this sort of menagerie of high-dimensional black holes, especially as the existence of these black rings violates black hole unities? You can have black rings with the same conserved charges as black holes, but different horizon topology, of course. Well, The starting point in terms of supersymmetric solutions was worked by Harvey Real, and then later with myself, in the context of classifying all the supersymmetrically asymptotically flat black holes in the ungauged five-dimensional supergravity. So this classification was constructed some time ago, and it came in two parts. Part one of the classification consisted of an analysis of the near-horizon geometries, and that was completely done. Those are fully classified. Part two of the classification consisted of using some of the global properties of these supersymmetric solutions. And it turns out that, as Harvey proved some time ago, that the only black hole which has the S3 event horizon topology is the BNPV black hole. It's not known that the only black object which has the S1 times S2 horizon topology is the black ring. There's a difference between the two. But in terms of the S3, that's now determined. Okay, so this is all in the ungauged theory. In the gauged theory, with a negative cosmological constant, we now know that there are the black holes with regular horizons. So these are constructed with Harvey Real and myself, and later generalized by Pope and others. So these are supersymmetric solutions which are asymptotically ADS5 instead of flat. Now, one can try and play the same game as in the ungauged theory and try and classify the lot using techniques which I described in the previous transparency. And indeed we tried this. We attempted first of all to classify all the possible near-horizon geometries. Unfortunately we weren't entirely successful. We managed to get a lot of conditions on the near-horizon geometries, but the result is much less clean than in the ungauged theory. But although incomplete, we did get enough interesting conditions to allow us to construct the first known regular black hole solution in this theory, which I described up there. And I should say that there are no known regular, with regular horizon, asymptotically ADS5 black rings, which are supersymmetric. And that's still an open problem. We know that there are no such solutions with two commuting rotational isometries, but that has to be input by hand. There may conceivably be solutions which have less symmetry, but we don't know that yet. So that's a very brief summary of the state of play in 5 dimensions. Now I'm going to start describing the structures that we found in type 2b 10-dimensional supergravity. And so before I go into the details, the gory details of type 2b supergravity, I'm just going to give some definitions for the actual structures that we found. So these are the geometries. So suppose I let n be a manifold equipped with some Hermitian form omega, say n complex dimensional. We know there's a unique connection with a skew-symmetric torsion called the Bismuth connection, with respect to which the metric and the Hermitian form are covariantly constant. And if we call h the torsion of this connection, then there's a very simple and nice relationship between the h and the exterior derivative of the Hermitian form omega as follows. H is just the contraction of d omega with the complex structure, and you can rewrite those in terms of these derivatives minus I delta minus delta bar omega. So the definition, the first definition is as follows. I'm going to call M to be K strong scalar with torsion if d bar of omega raised to the power of K is equal to 0. And because I know what H is in terms of omega, I can rewrite that condition in terms of the torsion H. It tells me that the exterior derivative of omega to the K minus 1 wedge H is equal to 0. So that's strong scalar, K strong scalar with torsion. There's a special case when K is equal to n minus 1, and then in that case the K strong condition is d bar omega to the power of n minus 1 is equal to 0. This is a scalar equation because this is a top form in n complex dimensions, and it's some second order equation, and it's been shown by Gutowski that one can always choose a particular conformal class given a Hermitian metric within which there's a representative satisfying this. So that's a special example. But now I'm going to impose additional conditions. I'm going to define a K-strong Calabi-Yau with torsion manifold to be a K-strong Kähler manifold for which the holonomy, the Bismuth connection, is in SUN. And the the punchline of this whole talk is that we're going to discover this structure. So the claim is that 2B supergravity near-horizon geometries give rise to a particular type of strong Calabi-Yau torsion structure, two strong Calabi-Yau torsion structure in 8 real dimensions. And we don't really know about these very much. So it would be interesting to understand them more. So now we need to...
I'm
yes.
sorry, just to make sure I'm
Yes.
remotely following. So supersymmetry tells you that essentially there is always some connection, generically not Levi-Civita,
Yes.
which would have a holonomy SUN if you are on a sort of 2n dimensional
Yes.
background. So your definition simply is about making sure that that connection is in question is bismuth connection, not
Yes.
some other connection.
That's correct.
And you are not looking only at backgrounds with purely Neveu-Schwarz backgrounds.
What I'm going to describe is 2B supergravity with just the 5 form turned on. So I'm going to kill off both 3 forms, and I'm going to set the axion and the dilaton to be constant. I'm going to talk a bit more about this later on.
So in other words, the torsion has nothing to do with the age.
No, the torsion. Well, if you we did heterotic supergravity as a sort of prequel to this, and because heterotic supergravity, the classification of supersymmetric solutions is compared to 2B is much more straightforward. And in that case, you have a natural 3 form, which appears in the Killing spin equation, and that gives you your torsion. That's a very obvious torsion. In this case, we start up with a 5 form. As we'll see, there is a 3 form encoded within the structure of the 5 form. But even that 3 form is not the torsion that I'm talking about here. It's a kind of a hidden structure. Oops. Okay, so that's the sort of geometry that we're aiming towards. And now I'm going to describe how you actually get it. And in order to do this, we need to work with a special basis and a special set of coordinates which are adapted to the near horizon region of a black hole. And so I'm not going to describe in full detail how you get this. This is done by Eisenberg and Moncrief. But I'm going to sort of give a very brief précis of how one constructs these so-called Gaussian null coordinates. And it's these coordinates that we'll do the analysis in. So we're going to assume that the space-time has a regular black hole event horizon, which is a Killing horizon of a Killing vector W. This is now an assumption. To analyze the near horizon geometry, we're going to work with Gaussian null coordinates, and we're going to assume that the future event horizon, H+, has a single connected component. We let sigma be a Cauchy surface of the exterior of the black hole with boundary S on the future event horizon. And, oh dear, I keep not correcting this. And we take Y to be local coordinates on S. This should not be 3, this should be 8. There's a minor typo here. S is an 8-dimensional manifold here. We let U be the affine parameter distance along the future directed null geodesic generator of H+, passing through S with tangent vector W. So this gives us an extra coordinate U in addition to the Y which we had before in some neighbourhood in H+, with W is equal to d by du. We then construct a null vector field M satisfying W dot M is equal to 1 and M dot X is equal to 0 for X tangent to surfaces of constant U, and we let R be the affine parameter distance along null geodesics which have this as a tangent vector. And at the end of the day, due to this you see that the Gaussian null coordinates are U, R and YI, and the metric has some special structure when you use these coordinates. In particular, d by dyi is tangent to the surfaces U is constant in H+, and so it's orthogonal to W at R is equal to 0. The horizon is located at R is equal to 0. And that means that the components Ui of the metric have to vanish when R is equal to 0, and this, so that means that GUI is R times HI, and H is going to be a 1 form on S, this manifold S, which is analytic in the R coordinate. Also, W has to be null at R is equal to 0 because it's a Killing horizon. And so for an extreme black hole, the UU component of the metric has an R squared here, times a function delta, where again delta is a function on S, but it also depends on R analytically. It doesn't depend on U, because d by du is killing. In principle, this could just be an R, and in that case, the black hole would have some non-vanishing surface temperature. But we're limiting ourselves to extreme black holes here, and so we're going to set the surface temperature 0, and so the first non-vanishing component of R, which appears here, is really R squared. And so, having adopted these coordinates, you can take a basis in which you have light cone coordinates, directions E plus and E minus, where E plus is du, E minus is dr plus rh minus a half r squared delta du. And so these give you this 2e plus E minus term here, together with the metric on S, which is gamma ij. And again, this depends on everything, nothing depends on U, but H, delta, and gamma ij depend on R and the coordinates of S, but they depend on R analytically. Now, this metric which I had in the previous transparency is well defined in some patch surrounding, containing the horizon, but now we're going to take a particular decoupling limit. So this is the metric which we had before, and the scalar delta, this one form H, and this metric gamma ij are what is called the near horizon data. If you know this, you know what the metric is basically. Now the decoupling limit is the so-called near horizon limit introduced by Havriel, and what you do is you rescale R goes to L times R, and U goes to L minus 1 times U, and then take the limit L goes to 0. And what this does is it throws away all of the asymptotic structure that you might conceivably have within the metric, so you can't tell whether the thing is asymptotically flat or anything like that anymore. But it retains the structure which describes the topology of the event horizon. So at least, although this is done to simplify matters somewhat, but we still keep a lot of interesting information. So we can see what sort of exotic event horizons appear in this theory. So we take the limit, and if you do this limit, you see the metric looks exactly the same, because, for example, there's a du dr term here, and you do this rescaling, and it doesn't change it at all. The only thing that changes is implicitly in this scalar delta, in this metric gamma ij, and in this one form H. When you take the limit, they no longer depend on R. So they just become dependent on these coordinates yi. And we're going to assume that the spatial cross-sections of this event horizon S, which have this metric, are regular and compact without boundary. The compactness is not going to play a very large part in what I'm going to discuss here, but there are some cases in which you can use it to simplify things a bit, and so I'll touch on those in a little while. So now I'm going to describe the theory, which is 2B supergravity with a 5 form. So we set the 2, 3 forms to 0, and we take the axion and the dilaton to be constant, but keep the 5 form F, which is self-dual, non-zero. We're going to assume that all the components of the 5 form in the Gaussian null coordinates are regular. Certainly that's true for the metric. We're going to assume this for the 5 form as well. And what this means is that some of the components vanish when you take the near horizon limit, and you're left with a rather simplified structure for F, this 5 form, in terms of a 3 form y. You find that F is equal to r du wedge dy plus du wedge dr wedge y plus the Hodge dual of y with respect to this 8-dimensional manifold S. And y is a 3 form on S which doesn't depend on u or r. That's what you find. I should, as I mentioned earlier, so we're finding a 3 form. This, however, is not the torsion. It's related to it, but it's not actually the torsion which I'm going to be constructing later on. Now, we want this 5 form to be self-dual, and we also want it to be closed. And when you impose that, you get conditions on this 3 form y. It has to be co-closed, and the 4 form dy minus h wedge y on S has to be anti-self-dual.
Sorry, where did H come from? Can you go back?
Well, this little h H is coming from this component of the metric. And that's what the phi form looks like. So now we want to analyse the supersymmetry. Now, if you kill off the three forms and the axion and the dilaton, then the killing spinor equations of 2D supergravity become reasonably simple. It's this, which is Navier epsilon. This is just the supercovariant derivative. And then there's the contribution from the phi form, which gives you this. I over 40 f times this 4 gamma term acting on epsilon is equal to 0. Now, the killing spinor epsilon, which appears in this killing spinor equation, is in fact regarded as a complex even differential form on R5. I'm going to describe what the Majorana Weyl spinors look like in terms of these differential forms in a little while. But first, it's particularly convenient to decompose the killing spinors, the killing spinor equations along the light cone direction. So we have two light cone directions, E plus and E minus, corresponding to the R and the U coordinates, basically, and we know completely the R and the U dependence of the metric. So we can integrate up these killing spinor equations in these particular directions. And if we split the spinor into epsilon plus and epsilon minus, which are annihilated by gamma plus and minus respectively, you can get expressions for epsilon plus and epsilon minus. Epsilon plus is phi plus, where phi plus is eta plus u times gamma plus times this operator constructed out of h, the one form h and the three form y, times this 3 gamma term acting on eta minus, and epsilon minus is this thing here, phi minus plus r gamma minus times phi plus, where phi minus is eta minus, and eta plus and eta minus are spinors which do not depend either on u or r. So we've integrated up these two components. You don't just get this, however, you get a number of algebraic conditions as well. In particular, you get two algebraic conditions acting on the spinor eta plus, which look rather unpleasant, but I'm not going to dwell on these. You also get a number of algebraic conditions acting on eta minus, but I'm not going to even write those down for a very simple reason, which will become apparent because I'm going to show that eta minus has to vanish. So those are those two components of the killing spinor equation dealt with. However, now I want to digress a little bit to just describe the structure of the spinors. So this will give us a way of classifying the solutions. We're going to find three families of solutions depending on a certain structure of the spinors. And so to codify that, I want to describe what the spinors look like. Spinors are complexified even differential forms on R5. And in terms of the Majorana spinors, they're constructed out of this basis. So we have the way they're written here. E1, 2, 3, 4 is just E1 wedge, E2 wedge, E3 wedge, E4. So that's a 4 form. And the spinors consist of formal sums of different degree forms. So this is 1 plus E1 wedge, E2 wedge, E3 wedge, E4. This is I times 1 minus that. And then we have these combination of two forms here and these two forms here. There are gamma matrices which appear in the killing spinor equation, and if one can adopt a null basis which is compatible with the Gaussian null basis, in which the metric looks like this, and the gamma plus is just root 2 times the contraction with the E5 direction. So that would just, if we acted with this would just give us EJ. This would just give EJ. Gamma minus is root 2 times the wedge product with E5, and gamma alpha and gamma alpha bar is simply creation and annihilation operators essentially. This is taking the wedge product with E alpha, and this is taking the inner derivative with E alpha. So
can you make a comment whether this is really useful and this differential form representation of spinors? Whether can you just work with standard?
Well, it's going to be it's useful in a number of things. It's useful because it lets you simplify the spinors using gauge transformations in a very explicit way.
Lorentz gauge?
Well, spin gauge transformation. So spin 9,1 times, well, in principle, U1 for 2D supergravity. And so it lets you simplify the spinors using these gauge transformations. And in particular, it's very useful for dealing with solutions with enhanced supersymmetry. So one can try analysing solutions with enhanced supersymmetry using the sort of bilinear approach in a sense, and that can be rather unpleasant in some cases. Whereas this actually gives you a slightly better set of tools for dealing with that. And I'm going to touch on very briefly on what happens when you take these horizons with enhanced supersymmetry later on. This is minimal supersymmetry. I'm really assuming n equals 2 in this case. N equals 2 because the killing spinor equation when you kill off the 3 form is linear over complex numbers. But
about one more question. So
Yes.
your killing spinor equation is from Gravitino.
yes,
The dilatino one is trivial.
that's trivial because I've set the axion and the dilaton to be constant and the 3 forms to vanish. And so that
There's
kills
no
off.
derivative acting on killing spin.
No, that's the other one is purely algebraic. It's got the gradient of the axion and the dilaton of the 3 forms, so that one goes away entirely.
This explains the field content. I mean, it would be more difficult to impose this constraint, would it?
It's doable. It's not undoable. It would just produce a much messier set of equations. So,
Good.
okay, right. So that's what the spinors look like, and now I want to consider a particular type of bilinear, which is going to be useful in what follows. So one can construct a one-form killing spinor bilinear from the spinor epsilon in the following way. So I'm not really describing what I'm doing here. C is some charge conjugation operator, and this is denoting some particular inner product. In fact, the angular brackets here simply correspond to the canonical inner product on the space of complexified 5 forms. One can construct this one form as follows, and then look at it, and one can prove that this one form is a dual in fact to a killing vector. And what we're going to do is we're going to identify this killing vector to be proportional to the killing vector W, which is what we assume exists from the structure of the black hole. So we're assuming we have a black hole whose horizon is a killing horizon of W. We don't have to do this identification. In principle, you could have black holes which have some supersymmetry when you take the near horizon limit, but aren't supersymmetric in bulk. And these examples of these things are actually known to exist, although not in 2B supergravity, I should say. But we don't have.
Killing vector is null, yeah?
Sorry.
Your killing vector is null.
The killing vector W is generically time-like outside. It becomes null on the horizon. So it has directions in both the E plus and the E minus directions. W squared, however, is proportional to R squared, so it becomes null when R is equal to 0. So that's what W is in the light cone basis, and we want to compute what Z is using one can actually write it out explicitly in the killing spinor explicitly using these forms and work it out and see what you get. And when you do that, if you impose the condition Z plus equal to 0 when R is equal to 0, because that has to hold for W, one can show that forces eta minus to vanish. You can write eta minus in terms of a linear combination of these differential forms which are on the previous transparency and work this out, and you find that eta minus has to vanish at the end of the day. When you impose this condition of vanishing, the conditions from the killing spinor equation from the remaining components orthogonal to the light cone directions simplify enormously. I can get them even simpler than this, but this is an intermediate stage. So one gets a sort of reduced Gravitino type equation involving the supercovariant derivative on curly S now, this is the 8-dimensional manifold, acting on this spinor eta plus, together with this algebraic mess acting on eta plus, together with those algebraic conditions I had on the previous transparency. And so this is now pulled out all of the conditions from the killing spinor equation in terms of this spinor eta plus. We're going to do even better though. And to see how this works, we're going to make certain gauge transformations which don't depend on U and R to simplify eta plus. And you can actually rotate eta plus into a form which is P times 1, I've missed out the 1 there, plus Q times E1, 2, 3, 4. where P and Q are complex space-time functions in general. So what one can do is one can work in this gauge, which, as you might appreciate, will simplify things a bit because we only have two functions now in the whole thing. And we can identify the remaining components of Z and W. And then you get various additional conditions. You find that the mod P squared plus mod Q squared has to be constant. And you find that the one form H, which appears in the metric, is related to the contraction of the 3 form with this almost Hermitian form omega. Now I say almost Hermitian because this thing doesn't have to be integral. Okay, and one gets one final condition, which is the relationship between the scalar delta, which also appears in the metric. So for example, going the wrong way. Delta. And that's the square of this 3 form y hat, where y hat is constructed from the 3, 0 bit of y, and this this contraction with the almost Hermitian form here. And chi is a 4, 0 form on S. So that's what you get from identifying the bilinears. Notice that delta is always greater than or equal to 0. You get that for free. So now I am coming towards describing the classification of these solutions. And they're classified according to the type of spin at eta plus. So recall that eta plus is p times 1 plus q times e1 to 3, 4, where p and q are some functions. And depending on special cases, special restrictions on these functions, eta plus is invariant under different types of subgroup of the spin group. So if mod p squared is equal to mod q squared, then eta plus is spin 7 invariant. If it's not, if mod p squared is not equal to mod q squared, and p and q are non-zero, then we're calling this a generic SE4 invariant spinner. And we're calling it a pure SE4 invariant spinner if either p or q vanish. Now I should say that although this is a gauge dependent statement on these functions, one can recast these statements as to whether something is spin 7 generic or pure in a gauge invariant way by constructing various bilinears. You can see in fact that, for example, the pure SE4 invariant spinner case corresponds to a certain gauge invariant 1 form spinner bilinear vanishing. And if mod p squared is equal to mod q squared, one can construct a spin 7 form in a natural way. So now I want to discuss these 3 cases one by one. I'm going to concentrate most of all on the pure SE4 case for a reason which I'm going to describe. But let's look at the spin 7 case first. This is very particularly simple because you can always choose a gauge for which p is equal to q. And when one goes back to those sets of equations that I had on the previous transparencies and plugs this condition in, at the end of the day the 3 form y vanishes, the 1 form h vanishes, delta vanishes, and so the 5 form has to vanish, and the spacetime is just R1, 1 times S, where S is a spin 7 holonomic manifold. So I'm going to not consider that anymore. I'm going to be particularly interested in solutions which have a non-zero 5 form, because otherwise there's no flux at all. Now I'm going to describe the pure spinor solutions. Now, these correspond to either p or q vanishing. However, one can see reasonably straightforwardly that 1 and E1, 2, 3, 4 are both related by an appropriate spin 8 gauge transformation, and so it suffices to consider eta plus to be proportional to 1. And because mod p squared is constant, we can, without loss of generality, take eta plus to be actually equal to 1. And when you do that, the algebraic conditions and also the conditions from the reduced Gravitino equation become much simpler. They look like this, and one can extract some interesting geometrical structure from this. So first of all, one finds the almost Hermitian structure omega is integrable. In this case, delta vanishes. Now, delta equal to 0 does not mean that the delta function that appeared in the full Gaussian null coordinate decomposition vanishes, because this is the function delta after one has taken the near horizon limit. So, for example, for something like the black ring solution, when you take the near horizon limit, you in 5 dimensions, you get a delta is equal to 0 condition at the level of the near horizon geometry. However, when you look at the full bulk solution of the black ring, the corresponding killing vector is not null in the bulk. It just simply becomes null at the horizon. It's simply a higher power of r which appears in front of in front of the delta in the Gaussian null decomposition. But at this level, delta vanishes after you've taken the near horizon limit. This is because certain bits of y vanish and p times q is equal to 0 because q is equal to 0 in this case. One finds that the one form h, which appeared in the metric, is in fact the Lie form of omega. And here I've written out the convention I've used for describing the Lie form in terms of the divergence of the Hermitian form omega. You also find that there's a natural Lie form associated with the real part of the 4, 0 form, which is defined by the real part of the 4, 0 form wedge, the Hodge dual of its exterior derivative, and then you take another Hodge dual to get a one form, and one finds that the conditions on the previous transparency imply that theta omega up here is equal to theta of the real part of chi defined by this. One also finds an explicit expression for the 3 form y in terms of the exterior derivative of the Hermitian form and its wedge product with the Lie form. And the last identity to impose is the Bianchi identity, df equal to 0. And you can see that after a bit of fiddling that this implies that the Hodge dual of d omega minus theta wedge omega is equal to 0. That's just co-closure of this. You also find that the exterior derivative of the Lie form has to be in SU4, but in fact one can show that this holds automatically as a consequence of the integrability of omega. So this is a somewhat simpler looking set of differential conditions. This is necessary and sufficient for the whole thing to satisfy the Killing spinor equations. One can do even better, however. But let's look first at the special case when the Lie form vanishes. That corresponds to little h vanishing. In this case, the Bianchi identity implies that omega wedge d star d omega is equal to 0. And if you integrate this expression over S, use compactness and the fact that you're assuming that there's no boundary for S, you get d omega wedge star d omega is equal to 0, which forces omega to be closed. And this forces y to vanish, and so that kills off the 5 form as well. And so this case corresponds to R1, 1 times the Calabi-Yau 4 manifold. We're not going to consider these anymore because, as I said before, we want to look at concentrating solutions with non-zero 5 form. But killing off the Lie form kills off the 5 form. So now I want to describe why there is a hidden torsion associated with this geometry. We have this condition on the 2 Lie forms. The Lie form of omega had to be equal to the Lie form of the real part of the 4, 0 form. One can see that this implies that there exists a connection nabla hat with a totally skew symmetric torsion H, which preserves both the Hermitian form and the 4, 0 form. So that means that S is a Calabi-Yau with torsion fourfold. Now, we know that the connection satisfying this condition is unique. It's just the bismuth connection with torsion, which I'd written down before. Requiring that the holonomy of this connection is contained in SU4, which is obtained from this, is equivalent to requiring the Ricci form of the connection vanish, which you get from this hatted connection. Now, this torsion H is hidden inside the 5 form in a non-trivial way. As I mentioned before, you don't get this from 3 forms of 2B supergravity because in this case, I've actually killed those off. It's coming from the 5 form, but in a non-obvious way. And this H is not equal to Y. It's closely related to it because this is what H is, and this is what Y is. They're both constructed in one way or another out of this Hermitian form, but they're certainly not equal to each other. That's what they are. The Bianchi identity can be written in terms of the torsion. One can rewrite it as requiring that omega wedge H be closed, or d bar omega squared is equal to 0. So in the language which we introduced earlier, this is telling me that this is a too strong Calabi-Yau with torsion structure, as I said some time ago. So this is where we're getting this structure from, and that's the whole lot. So the summary so far. The spatial cross-section of the pure spinor solutions is a compact 8-dimensional manifold S with a Hermitian structure omega. And this is further constrained by requiring that the Ricci form of the bismuth connection vanishes, so it's Calabi-Yau with torsion, and from the Bianchi identity, d bar of omega squared is equal to 0. And this gives us the too strong Calabi-Yau with torsion structure. Once you've got this, you know everything. This is what the metric is in terms of the Lie form of this manifold S, 2 du times dr plus r theta plus the metric on curly S with this structure, and the 5-form F is given by this expression in terms of this 3-form Y, and Y is also fixed in terms of the Hermitian form on curly S by this expression here. So that's the solution for the pure spinor case.
So at the start of the talk, you spoke about case-strong Calabi-Yau torsion structure, yeah?
Yes.
So where does the 2 arise in this?
The 2 arises because of this 2 in here. In general, it would be K. Yeah. So in principle, you can stick whatever number you want in there, but in our case, we're getting 2. In the heterotic case, you get 1. If you do the near horizon analysis in the heterotic case, you get 1. 2b, you get 2. Now, I should mention briefly, this is the pure spinor case. I dealt with the spin 7 case earlier. I killed that off quite quickly. The 5-form has to vanish for that. There is, however, another case, because there were 3, which is the generic SU4 case. This is somewhat trickier to deal with, and this is still slightly open. But one can show using compactness of the cross of the 8-manifold S that if one has a generic SU4 spinor eta plus, which never becomes pure at any point, so these functions P and Q are always non-vanishing, then the 5-form would vanish in that case as well. So in principle, one could have a class of solutions, and one would probably expect class of solutions for which in the generic class for which P and Q might vanish at some point, and that's outside of our classification at the moment. We don't really know much about those. But if you have a generic SU4 structure which is never pure in that sense, then again it's perhaps not interesting because the 5-form vanishes, and it's just again R1,1 times Calabi-Yau 4 manifold. But I'm not going to go into that detail because it's not particularly illuminating. So now I'm going to discuss some examples. I should mention first of all that there are lots of black hole solutions, well, a number of black hole solutions in 5-dimensional gauge supergravity, which you can lift to 2b supergravity. You can work out what the near horizon structure of the 5-dimensional black holes are in terms of the language which I've described here in terms of this near horizon data in the Gaussian null setup, and you can lift those up to corresponding near horizon geometries in 2b supergravity, and you can work out what the associated 2-strong Calabi-Yau torsion with structure is in terms of all of the lifting data, and we've done that, and it works quite nicely. But these solutions are perhaps not, well, they're interesting, but I'm not going to look at those in any detail. I'm going to concentrate instead on ADS3 solutions. So as I mentioned earlier, you can write solutions which are warp products of ADS with some internal manifold in the language of this near horizon geometry. And what I want to do now is to just describe how this fits into this picture here, and pull out all of this Hermitian structure with this 2-strong structure as well. So what we're going to do is look at ADS3 solutions, and we're going to write it in terms of the Gaussian null data, and in particular the light cone directions 2 du dr plus 2r du theta. We're going to require that this be conformal to ADS3, but I'm going to talk about that in a little while. First of all, I want to decompose the 8-dimensional manifold S into a 1 plus 1 plus 6 way of doing things. So I'm going to choose Z to be a closed 1 form. I'm going to choose omega to be some other 1 form. I'm going to have a conformal factor A squared in front of them, and I'm going to have ds squared B, which is a metric on a 6-dimensional base space. I'm going to assume that the lead derivative of everything with respect to Z vanishes up here, and I'm going to take the Hermitian form omega, which I need in order to construct this near horizon solution, to be a squared Z wedge omega plus omega B, where omega B is a Hermitian form on this base space B here. Now, as I said, we're going to require that the bit which is 2 du dr plus 2r du theta in the metric should be conformal to ADS3, and this gives us a condition on the Lie form to be theta is minus 2 over Lz minus d log a squared. And then well, one can see if you plug this in then and make an appropriate coordinate transformation, you get something which is conformal to ADS3. It's going to be useful to decompose the exterior derivative of omega b, which appears here, in terms of omega wedge psi, where psi is a 1 form on a 2 form on b, and eta is a 3 form on b, and integrability of this of omega imposes a number of conditions. Psi and dw have to be 1, 1 with respect to omega b. dw has to have no direct has to be orthogonal to w, and eta has to be 1, 2 and plus 2, 1 with respect to omega b. And if you decompose the exterior derivative of a squared in a direction along w and another direction orthogonal to w, then the torsion of the Bismuth connection, which preserves this thing here, is given in terms of these in terms of rho z w and a squared like this. It's not very nice at the moment. The condition on the Lie form theta, written there, decomposes into these conditions here. For example, the trace of psi with respect to omega b is minus 2 times the function f, where f is the thing which appears in this d log a squared. And also you get conditions on the trace of dw and this object here. So that's the Lie form condition. There are also conditions obtained from the two strong conditions. So this is d bar of omega squared equal to 0, and one can decompose them and you get 4 conditions, 1, 2, 3, 4 like this, where I've decomposed the contraction of rho with the complex structure IB in terms of W wedge mu plus lambda and like this. So this is what you get. It's not particularly necessary to look at them in too much detail. There is one more condition obtained by the vanishing of the Ricci form, which gives you this condition in terms of the Lie derivative of the logarithm of the determinant of a 7-dimensional metric, which is obtained from a squared w squared plus the metric on b. So that's just ignoring that's just removing the z direction from the metric on s and restricting yourself to this. And this condition on the Ricci form implies that these two conditions on G7. Okay, so that's what you get from the supersymmetry when you embed the ADS3 solutions in this language. And this is what the metric looks like. This is just the metric on S, and this is the metric on this is the du, and this is the Lie form term. And this is what the 3 form Y looks like, and once you know Y, you can construct the 5 form. So this is, in a sense, everything associated with these solutions. However, the key point is that although the metric has the ADS3 symmetries, the 5 form at the moment does not. So if you impose the SO2 symmetry on the 5 form, you get additional conditions. In particular, this 2 form psi has to vanish, this function f also has to vanish, and this combination eta plus rho wedge omega b also has to vanish. And the Bianchi identity simplifies from 4 equations just to 1. dd bar omega squared is equal to 0, just becomes the Laplacian of the logarithm of a is equal to a to the minus 2 times minus 1 over L squared plus an 8th dA squared omega contracted with itself, where this is the Levi-Civita connection on the 7-dimensional X7, which has this metric here. If you analyze carefully the Einstein equations, one can pull out an isometry of X7, which is in the W direction. It's a squared W, and the Lie derivative of a and W with respect to this isometry vanishes. And if one makes a conformal rescaling of B to B circle, like this, so this is just to say the a squared omega is the same, but I've rescaled the s squared b to be a to the minus 2 ds circle squared b circle, then the conditions on the geometry force B circle to be a Kähler manifold with this to be the Kähler form, and the Ricci form of this Kähler manifold is just proportional to dw. There is one particularly interesting equation which you get at the end of this. First of all, you can look at the conditional Lie form, which relates the Ricci scalar of B circle to the conformal factor A by this. So the Ricci scalar is A to the minus 4th times A over L squared, and the remaining condition obtained from the Calabi-Yau with torsion structure is this highly nonlinear differential equation involving the Laplacian of the Ricci scalar equal to half times the Ricci scalar squared minus the contraction of the Ricci tensor squared. And this equation, I should say, is not new, but it's been found before in terms of the ADS solutions in 2B supergravity by Naku Kim and others some time ago.
In that classification, what field content did Nagu have? Do you remember?
This one was just the same.
It's just a 5 form. So
Yeah.
there's no
So, but with the symmetries, of course. I mean, so the first stage which I described is the case when the metric has the symmetries, but the 5 form doesn't, and that produces some rather ugly-looking conditions. But if you impose the symmetries, then fully, then you get this. And this is particularly interesting in terms of Ricci flow, I have to say. Now, I mentioned briefly before the issue of enhanced supersymmetry, which is what this spinor geometry approach can help you a lot with. And we've shown that if you consider pure spinor solutions, for which all possible linear combinations of the spinors stay pure, then one can completely classify the solutions. So this is work done by myself and George Papadopoulos some time ago, and there are only 2 cases. In the first case, one can have solutions preserving n equals 4 supersymmetry and with non-zero 5 form, and these are either ADS3 times S3 times T4 or ADS3 times S3 times K3 with S1 times S3 times T4 or S1 times S3 times K3 as the 8-dimensional manifold curly S. For solutions with more than 4 supersymmetries, these are all flat R1,1 times T8 with vanishing 5 form. Now, I should say this does not this analysis doesn't contain all of the solutions a priori with enhanced supersymmetry, because, as I mentioned before, we've thrown away the generic SU4 cases. So I've deliberately restricted the analysis here to pure spinor solutions for which all the linear combinations of the spinors stay pure. So if one includes the generic SU4 class of solutions, which could conceivably become pure at some point, but not necessarily everywhere, then there may be many more solutions. But as a first attempt to classify, restricted to the pure spinor case, we've managed to make a bit of progress. And so these are the conclusions. We've classified all the pure spinor near horizon solutions in 2B supergravity with non-zero 5 form. And we've shown the spatial cross-section of the horizon are 8-dimensional compact manifolds emitting integral Hermitian structure omega such that Ricci form of the Bismuth connection vanishes and d bar of omega squared is equal to 0. And once you're given this so-called too-strong Calabi-Yau with torsion structure, you know completely the rest of the solution, and you can determine it. And it turns out that all of the 5-dimensional uplifts of black holes can be embedded in this formalism, and all the known warp product ADS solutions can be also written as particular special cases in near horizon geometries, and some of these have some rather curious structures associated with them. So that's where we've got up to, but there are many open questions. As I said, we need to understand properly the generic SU4 case, and that would be an interesting to do. What we've done up to now, of course, is only the near horizon analysis. We need to extrapolate, see if one can extrapolate in a meaningful way these near horizon geometries away from the near horizon limit to construct some sort of full black hole solution. It needn't be asymptotically flat, we don't really have any control over that at the moment, but in principle one could try and do it. One could include more field content, like non-zero 3 forms, non-constant axion, and a dilaton. And lastly, I just want to mention briefly this equation which we had earlier. So recall if we looked at the ADS3 solutions, and you impose the SO2, 2 symmetry for the metric and for the 5 form, at the end of the day, after a bit of conformal rescaling, we ended up with a Kähler manifold, which 6-dimensional Kähler manifold, whose Ricci scalar satisfied this equation. Now, Chen and Tian have looked at Ricci flow on Kähler manifolds, and this equation is reminiscent of one of the equations they get. So they get the partial R over partial T is the Laplacian of R plus the Ricci tensor squared minus R, where T is the evolution parameter for the flow. This is somewhat similar to this, however, the coefficients are slightly different, and also the power of R is different. Here is just an R squared, and here it is just an R. And so it would be rather interesting to understand if there's some interpretation of this sort of equation, which has also, as I said, been found in the context of the ADS3 solution some time ago, in terms of some other geometric conditions. Okay.
Questions? Comments? I have one question about this pair of equations. So the second one, as you said, is a flow equation in a parameter t, right?
Yes.
But now on the right side, this first term delta, is that just grad squared?
Yes. Oh,
So,
yes.
so it is actually the same combination of grad squared R and Ricci squared, right?
Well, it's not. Yeah, Ricci tensor squared, yes.
So it is the same combination that you have above.
But the coefficient of the R squared term is different, and the power.
No, there's no R squared term in this, right?
No. But yeah. So yeah.
So
the
in
third
fact,
term-
so it seems that if you use, I mean, you can't really compare these because one is a flow equation and
Yes.
one is just an equation. But it is striking that the combination of the things which do appear in both equations is the same, not with different coefficients.
it's,
So the flow equation in your geometries becomes very simple. It just has R squared minus half R.
Exactly. So
Or
it becomes a
half R
scalar.
squared
If you
minus R.
use the upper equation, then the lower equation becomes a scalar equation for just one variable R.
That's true.
It looks like a solvable differential equation.
It's not a nice looking equation, I have to say.
Any more questions? It's still early, maybe I can ask one more. So you mentioned something about warped ADS compactifications. Could you just sort of say which ones which ones are known, or just briefly mention?
Well, the ADS5 ones can also be rewritten quite easily in this formalism.
Mm-hmm.
Doing the even ones is a bit tricky. We haven't managed it's simply the issue, the starting point really, because you start off and you want to decompose the 8-dimensional thing into the Z would always be there probably, but then you need to introduce extra directions W. So in this case we only need one for ADS3. We've done ADS5. I think there are no ADS7 written like this. But the even cases.
There's a known ADS6 cross S4 warped solution, right?
I think,
just one.
yes.
It's in massive type 2A, isn't it?
Yeah, it's in massive. Yeah, that's true. So it wouldn't appear. No, sorry, not for type 2B. You're right.
I can ask a question. So this ADS3S3 geometry, I mean, usually it's sourced by a 3 form, Ramon 3 form, or Never-Schwarz B field or something like that. So the one sourced by the 5 form flux, I mean, it should be due to the same superconformal field theory, but what's the transformation that you do in the case of K3 that brings, that converts the 5 form into a 3 form? Is that known? I mean, the 5 form can wrap a Calabi 2 cycle inside
That's true.
the K3.
Not clear what you do in that case.
Just something I'm curious. I mean, for elliptic K3, there's a mirror symmetry transformation which we're put in,
Yes.
or generally.
Generally, it's not clear.
Yeah.
Okay, any more questions? If not, let's thank the speaker again.